String theory has always been this kind of holy grail in physics, the one idea that could finally be a theory of everything. But there's a pretty big catch. We can't actually test it, at least not yet. And that's not just a small technical problem. No, it actually makes us ask a really fundamental question about how science itself is supposed to work. So yeah, how does science really work? Is it this neat, orderly checklist you follow? Or is it something, well, a little more flexible, a little more creative? Especially when you're trying to explore parts of the universe that are way, way beyond what our best tools can see. Let's dig in.
I'm sure you've all seen this before, right? Probably in a high school science textbook. It makes science look like a simple four-step recipe. And look, it's a useful starting point. But it completely papers over the messy, intuitive, and frankly, sometimes frustrating way that huge scientific breakthroughs actually happen. And that brings us right to the heart of the issue with string theory. See, the theory describes things happening at energy levels so incredibly high that we just can't get there with our current technology. So if you can't test your hypothesis, are you even doing science anymore? This is where that simple textbook model just completely falls apart. Okay, to really get what's going on, we have to understand the two main pillars that hold up all of science. It's not just a one-way street. It's this constant back and forth, a conversation between the world of pure ideas and the world of cold, hard facts. So on one side, you've got theory. This is the realm of elegant math, of connecting big ideas and making these bold predictions about how the universe should work. And on the other side, you've got experiment. This is what keeps us honest. It's all about observation, gathering data, and seeing what the universe actually does. Real science, the good stuff, happens in that dynamic dance between the two. And Einstein himself nailed it with this. You absolutely need both. I mean, a theory that has no way of connecting to reality, it's just a fun game with numbers. But a bunch of experiments without a theory to explain what they mean, well, that's just a random list of facts. You need both to truly see. Right. So, if experiment is so important, how do we even decide if a theory is a real contender? Well, that brings us to this really powerful idea from the philosopher of science, Karl Popper. You can think of it as a kind of bouncer at the door of club science. Here's the key idea. For a theory to even be considered scientific, there has to be some kind of experiment you could imagine doing that could prove it's wrong. It's not about proving it right. It's about whether it's capable of being proven false. Let's make this super simple. The statement, "the sun will rise tomorrow," is totally scientific. Why? Not because we're sure it's true, but because it's testable. It makes a risky prediction. If we wake up tomorrow and it's pitch black outside, bam, hypothesis falsified. But a claim that can't be proven wrong no matter what happens, well, that's just not playing by the rules of science. I love this quote. It just perfectly captures the beautiful brutality of it all. You can have the most elegant, stunningly beautiful theory in the world, but if one single ugly little fact from an experiment says it's wrong, then the theory has to go. That's the discipline that makes science work. And this, of course, puts string theory right in the hot seat, because right now it doesn't pass the falsifiability test. Some critics are arguing that it isn't really science at all. This has sparked some legendary, though usually friendly, debates between brilliant physicists like Leonard Susskind and Lee Smolin. Is it a beautiful idea just waiting for the technology to catch up, or is it drifted off into philosophy? But this whole debate isn't just about one theory. It's really about how science itself evolves. To get the big picture, we've got to zoom out a bit. Science doesn't just inch forward one little fact at a time. Every once in a while, it has a full-blown revolution. And the historian and philosopher Thomas Kuhn gave us a fantastic way to think about these epic shakeups. Kuhn called it a paradigm shift. And this isn't just about tweaking a few equations. It's a fundamental change in how scientists see the world, the basic assumptions, the questions they ask, the tools they use. The classic example is the jump from Newton's physics to Einstein's relativity. They had to completely rebuild our understanding of space and time from scratch. Kuhn saw science moving in a cycle. Most of the time, we're in a period of normal science, where everyone's just solving puzzles within the existing framework. But then, anomalies start popping up, little weird results that the old theory can't quite explain. When enough of those pile up, you get a crisis. The old theory just isn't working anymore. And it's out of that crisis that a revolution can emerge. A new paradigm is born, and the whole cycle starts over. So if you're a physicist today, and maybe you feel like you're in one of those crisis phases, where the experiments can't quite guide you to the next big theory, what do you do? Where do you even look for answers? Well, for many theorists, the answer lies in one of the most profound and beautiful ideas in all of science: symmetry. Now, in physics, symmetry is a really deep concept. It basically means that when you change something, like your location, or the direction you're facing, or even the time on the clock, the fundamental laws of physics stay exactly the same. It's a powerful statement about how consistent and reliable the universe is. And these are symmetries we just take for granted. The law of gravity works the same in your bedroom as it does on Mars. That's translational symmetry. An experiment will give you the same result if your lab is facing north or south. That's rotational symmetry. These aren't just neat ideas, they are the absolute bedrock of modern physics. But here's where it gets really cool. Sometimes the most interesting stuff happens when a symmetry is broken. Think of a perfectly round, symmetrical droplet of water. But when it freezes, that simple symmetry breaks and it forms an intricate, unique snowflake. In physics, it turns out that many of the complex things we see in the universe come from these moments of symmetry breaking. And that brings us all the way back to string theory. For the mathematics of the theory to even work, to be stable and consistent, it demands a very special, very powerful kind of symmetry called supersymmetry. This isn't just something theorists added because it looks nice, it's a critical ingredient. They are following this deep principle of mathematical beauty as their guide, even when they can't run an experiment. So what's the big takeaway from all this? Well, the scientific method clearly isn't that simple checklist we all memorized in school. It's so much more. It's a dynamic, deeply human endeavor. It's about wrestling with the unknown, using powerful ideas like falsifiability to keep ourselves honest, surviving revolutionary paradigm shifts, and sometimes just following deep principles like symmetry when all the other lights go out. Which leaves us with one last big question. As our theories start to explore realities that are just getting harder and harder to test directly, does our definition of science itself need to change? Are things like mathematical consistency and elegance enough to go on? Or is experimental proof always the final word? String theory isn't just challenging our view of the cosmos, it's challenging how we think about science itself.